Today we are focusing on Chapter 7.7, which is Quadratic Systems. And so I want you to take a second and think back to a linear system. When we had linear systems back a few chapters ago, or when you were in Algebra 1, we were looking at two lines that existed on the same coordinate plane. And whenever we had two lines on the same coordinate plane, we were always interested in their point of intersection, if it even existed. So in this case, looking at this point of intersection here, I'm just going to go ahead and guess, say 2, 1 is the point of intersection. Here, we're dealing with multiple points of intersection because it seems like the top graph is an ellipse of sorts. So let's say it looked kind of like that. The bottom, if you understand your conic sections, that's going to be a hyperbola. So let's just say it looks like that. I don't know what it really looks like, but we know that when there's an ellipse and a hyperbola, there are potentially four distinct points of intersection. So knowing your conic sections will tell you how many points of intersection or how many answers you should anticipate. So there are a couple of different ways you can solve a quadratic system. First way, you can graph. Honestly, that's pretty ineffective. Solving these algebraically is a lot more effective. So I'm going to go ahead and rewrite my top equation here. And the bottom equation I'm going to go ahead and manipulate. I'm going to go ahead and subtract 9x squared from both sides. And so I get negative 9x squared plus y squared. And at the same time, I'm going to add 16 to both sides. So that's all going to equal positive 16. I'm going to place this underneath my original equation here. Okay, so it's just like solving a linear system. So what I'm going to do is I'm going to go ahead and multiply the top by negative 1. That gives me negative 5x squared minus y squared equals negative 30. Those are going to cancel each other out. I get negative 14x squared equals negative 14. If I divide both sides by negative 14, I get x squared equals 1. Taking the square root of both sides, I get x equals plus or minus 1. Now it's important to have that plus or minus because you have to plug each one into the original equation to figure out where your points of intersection are. So the way a quadratic system is different is that when I plug something in, I automatically determine its coordinates. And I'll show you guys what that looks like right now. Let's go ahead and use the top equation as our base of plug-in. So if I plug positive 1 in first, I'm going to get 5 times positive 1 squared plus y squared equals 30. That is 5 plus y squared equals 30. I'm going to move a little bit faster. Y squared is going to equal 25. Y is going to equal plus or minus 5. Okay, what does that mean? It means that when I plug in positive 1, I get two answers, plus or minus 5. Those you should already write out in coordinates, that way you don't get confused. 1 outputs an answer of 5, and 1 also outputs an answer of negative 5. Sometimes in the book you might see 1 comma plus or minus 5 as your coordinates. All right, that's fine too. Let's change colors for the next example. If I plug in negative 1, I'm going to get 5 times negative 1 squared plus y squared equals 30. Well, this is positive 1, so I still get 5 plus y squared equals 30. Y squared still equals 25, and y still equals plus or minus 5. Now, even though you got the same value for y, it's still a different answer, because remember, you plugged negative 1 in to get your positive 5, and you plugged in negative 1 in to get your negative 5. So the collective answer could be seen as negative 1 comma plus or minus 5. Clean that up. All right, so these are your answers here. So remember, you have to be very careful about how you plug things in during a quadratic system. That's the only thing that could really kind of mess you up in this section. Other than that, it's pretty self-explanatory. Let's do a couple more examples and see if we can't lock this down. Number 2, if I give you a quadratic system of y equals 2x squared, and then y equals x plus 3. So again, go ahead and just visualize what this is. Y equals 2x squared, that's a parabola. And y equals x plus 3, that's a line. So I'm looking at possibly 2 points of intersection. Because I have y isolated in both, I'm going to go ahead and use substitution. I'm going to plug my 2x squared into here. So what I get is 2x squared equals x plus 3. Because I have a quadratic equation now, I'm going to go ahead and set everything equal to 0. So what I get is 2x squared minus x minus 3 equals 0. Let's go ahead and factor that. 2x and x, it's going to be 3 and 1, negative, positive. So therefore, x is going to equal 3 over 2 and negative 1. Oops, not negative 11, negative 1. And so let's go and save those answers and plug them in. I say that plugging them into the top is going to be easier. So let's go ahead and make our next section. I'm going to go ahead and change colors again like we did the last time. Y equals 2 parentheses 3 over 2 quantity squared. This is 9 over 4 multiplied by 2, 18 over 4. Let's see here. Those are going to cancel out. I get a 2 on bottom, so y equals 9 over 2. Now what that means is that my coordinates are 3 over 2, comma 9 over 2. That's my first point of intersection. My next point of intersection comes from when I plug negative 1 into that thing. So y equals 2 times negative 1 squared. That's a piece of cake. Y equals 2. That means that my point of intersection here is going to be negative 1, comma 2. These are your answers to the quadratic system. Okay, number 3 here. Just like a linear system, sometimes we have to manipulate 1 in order to make it match, and that's fine. We get 4x squared plus y squared equals 100, and then on bottom we're going to get negative 4x minus y squared equals negative 20. Now the reason why I included this as an example is because I want you to make sure you do not fall into the trap of making this 0x squared. 4x squared minus 4x is really 4x squared minus 4x equals 80. I'm going to go ahead and divide everything by 4 to reduce this. I get x squared minus x equals 20. I'm going to subtract 20 from both sides. That is x squared minus x minus 20 equals 0. So this factors into x minus 5 times x plus 4. So x equals 5 and negative 4. So now I take that information, I plug it in to one of my equations. So I'm going to go ahead and just choose the original bottom. Let's go and choose the original bottom. So if I plug in 4x, x being 5, plus y squared equals 20, what I get is I'm sorry, moving a little too fast there. 20 plus y squared equals 20. Those are going to cancel each other out. Y squared equals 0, therefore y equals 0. Let's try and plug negative 4 in and see what happens. 4 times negative 4 plus y squared equals 20. Move this over. This is negative 16 plus y squared equals 20. Y squared equals 36. Y equals plus or minus, plus or minus 6. And I kind of broke my cardinal rule there. I didn't put in my coordinates right as soon as I solved it. This is negative 4 comma 6, negative 4 comma negative 6. And on the red side, I have 5 comma 0. Now, important note about this problem here. We seem to have an ellipse and a parabola. So ordinarily, you would think they'd have 4 points of intersection, right? 1, 2, 3, 4, but they only seem to produce 3. When that happens, what you have is a parabola that barely grazes an edge of the ellipse. All right, so that's what you really have. May not be exactly like that picture, but this is the dynamic that I want you to see, that grazing effect. All right, let's do another one. Okay, with number 4, let's go ahead and square both sides. That way I can start eliminating the y's. Now, be careful when you square everything. This y squared is going to be y squared. But this x squared needs to be squared as a group. So this is really 49 minus 14x squared plus x squared. And we got y squared plus x squared equals 9. So let's go ahead and move some things over. Let's go ahead and subtract x squared from both sides and add 14x, and that should not be squared. So this is really y squared minus x squared, right, because those go away, plus 14x equals 49. This bottom thing is really y squared plus x squared equals 9. Well, the x squareds are going to cancel each other out. I get 2y squared plus 14x equals, looks like 58. Now from here I've got a y squared and a regular x. This thing cannot be factored. So therefore I am stuck, and therefore it is no solution, which means that this line right here and this looks like circle do not intersect at all. Okay? Let's do one last one, and then we'll call it. Okay, let's do number 5 here. If I do 3x squared minus y squared equals 9. Okay, just like last time, I'm going to go ahead and multiply the top by 2, so I get 6x squared minus 2y squared equals 18. I get x squared plus 2y squared equals 10. Those are gone. I get 7x squared equals 28. X squared equals 4. X equals plus or minus 2. Now I'm going to choose one to plug it into. I'm going to go and choose the bottom one. I'm going to change colors here and make my little barrier. So if I plug in positive 2, I get 2 squared plus 2y squared equals 10. That is 4 plus 2y squared equals 10. I'm going to move a little faster again. This is 2y squared equals 6. Y squared equals 3, so y equals plus or minus rad 3. So therefore, my points of intersection when I plug in 2 are 2, comma, rad 3 and 2, comma, negative rad 3. Okay, next one. Let's plug in negative 2. So negative 2 here, squared plus 2y squared equals 10. So this is, again, 4 plus 2y squared equals 10. I think you guys kind of know the ending to this movie here. Y squared equals 3, y equals plus or minus rad 3. So therefore my answer is going to be negative 2, comma, rad 3, and then negative 2, comma, negative rad 3. And there are your points of intersection between what looks like a hyperbola and an ellipse. All right, systems of quadratic inequalities require us to graph. So similar to the systems of linear inequalities, we're trying to find the shared shading of what's going on in these two graphs here. So why don't I go ahead and just put in the graph here and just go ahead and sketch each one. What I've got is I've got a circle with the center of 0, and it has a radius of 5, so I move out 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's 4, and then 1, 2, 3, 4, 5, okay. And I believe this one needs to be out more. Okay, so now let's go ahead and just draw this circle real quick. And now I need to find where it's being shaded. Well, go ahead and just pick a test point. If I choose 0, 0, if I plug 0 in for x and 0 in for y, 0 plus 0 is less than 25. That is true. Therefore, my shading is going to occur inside the circle, right? Inside the circle here. Okay, let's go and convert our line. This is really 2y is greater than or equal to negative x plus 1. If I divide everything by 2, what I get is y is greater than or equal to negative 1/2 x plus 1/2. So that's plus 1/2 is right here, and it moves down 1 to the right 2. So it looks like I have a linear equation that does this. And from here I can go ahead and figure out where I am shading. The shading is above the line, which means that all of that shading is going to happen right here. So again, on a system of inequalities, we want to find the shared shading. It looks like the shared shading is happening inside this little hemisphere right here. So this is where you want to be for your shared shading, where the purple is. Okay, don't let the bottom threaten you. That is really 9x squared plus 4y squared is less than or equal to 36. We are dealing with two ellipses, so let's go ahead and convert. I'm going to go and divide everything by 36. All right, I'm going to divide everything by 36 again. So my real equations are going to be x squared over 9 plus y squared over 4 is greater than or equal to 36. And on the bottom, I'm going to get x squared over 4 plus y squared over 9 is less than or equal to 36. So let's go ahead and graph these two and see what happens. Okay, the top one's going to be the red equation. So here my centers are both at 0, 0. My top equation, my major axis is along x. So I'm going to go out 1, 2, 3, 1, 2, 3, and then up 1, 2, down 2. And I'm going to go ahead and circle that. I need to choose a number for my test point. I'll go ahead and choose my center, so 0, 0. This is 0 and 0. 0 plus 0 is not greater than 36, which means that my shading is going to occur on the outside of the ellipse. On the outside of the ellipse. Let's go ahead and graph the blue ellipse. My major axis is going to be underneath y, so I'm going to move up 1, 2, 3. Down 1, 2, 3, and I'm going to move to the right and left 2. And so I have this tall ellipse here. And so even though the shared shading isn't going to be too apparent, let me see if I can just kind of shade over it again. If you guys remember, all the shading for the ellipse here is happening outside of the red ellipse, and that includes this area. And I think you guys kind of know where I'm going with this. Because for the blue ellipse, if I plug in 0, 0, that is true, which means that I'm shading inside the ellipse. And so therefore my shared shading is going to happen on the top and on the bottom. You know, I should choose something a little more distinctive. The top and the bottom of where the ellipses intersect. Okay, and that's pretty much it for quadratic systems of inequalities. All right, we'll see ya.